Hi, everybody. This is Dr. Nigro with the Physics Fundamentals Screencast. This is another one in our series dealing with work and energy. This one's specifically going to look at the calculation of work when you are applying a variable force. All right, we've already looked at calculation of work in the presence of a constant force, and that's where work is equal to the absolute value of force times the absolute value of displacement times the cosine of the angle between that motion and the force. Work with a variable force is going to be different. The formula is not going to be the same, so you're going to need to make sure you're paying attention to your problem so you know which situation you're in. All right, a variable force occurs when you have objects like springs or rubber bands, basically any object where you need to increase the amount of force applied to continue increasing your displacement. All right, so think about a rubber band or a spring. All right, when you stretch it, at first it's pretty easy to stretch, but then the further and further you try to stretch it, the harder and harder it gets. That harder and harder aspect, that is the increasing amount of applied force that you're having to produce in order to get that band to continue stretching like that. Okay, so when we talk about a spring, all right, so let's say we have a spring that's attached to something like a wall, and then we put something we can grab like a block. All right, there's force in your spring called the spring force, F sub S. All right, if we then take that spring and we grab the block and we pull the block out, we apply a force, all right, that's going to stretch that spring. And this distance between where it was without any pulling and where it is after we pull it, this is our displacement. All right, now we use the D with constant force. For our variable forces, you're going to see it most often as X, but it means the same thing. It's the displacement. All right, in this situation, our applied force is working against that spring force. All right, and the applied force can be just us pulling, or you could set it up vertically where your spring is hanging and maybe you hang mass from the end of your spring. And if that's the case, then gravity pulling on that mass is what's going to apply that force. All right, now we have to be careful. All right, when we pull it out like that, if we let go, it's going to snap back when we have the horizontal situation. And that's because that spring force is present and it wants to be back at its equilibrium position. All right, but you can over stretch your spring. And when you do that, it won't snap back anymore. All right, that's called reaching the elastic limit of your spring. And each spring and rubber band is going to have very different values for that, depending on what they're made of and depending how large they are, how small they are, how many turns you have in the spring, all kinds of things. Right? But if you think about a rubber band, you can pull it and you can continue to pull it. And maybe eventually when you let go, it's kind of deformed. It doesn't snap back to what it looked like originally, or you break it. I mean, that could be bad too. All right. So if you overstretch it, you've reached that elastic limit. And you want to make sure when you're doing experiments with springs or rubber bands that you stay underneath that elastic limit. Because once you go over it, then we start to get stuff going on with our springs that's not predictable. Okay. Now there's a law that governs how force and displacement interact when it comes to variable force. And that law is known as Hooke's law. All right. You often conduct a lab in physics that looks at Hooke's law where you have the force that's applied, all right, versus that change in position. All right, put my units up here. All right, and what you find is that at 0, 0, you get a linear relationship between these two variables. All right, and that linear relationship is equal to the force equal to some slope of that line times x plus our y-intercept, which should be 0. All right, now this slope is specific for each individual spring, is called K. All right, and that is our spring force constant. All right, that spring force constant is going to have units of newtons divided by meters, which makes sense because it's force divided by x. All right, and what that spring force constant really tells us is how much force is required to stretch that particular spring or rubber band 1 meter. All right, so the larger your spring force constant values, the more force it's going to be required to stretch it. That means the tighter or the less stretchy that particular spring or rubber band. The lower your K value, the easier it's going to be because it's going to require less force. All right, so we could have a plot that looks like the one I drew, or maybe we have something that looks like this, where our K value is greater, or we could have something that looks like this, where our K value is lower. All right, that tells us something about that particular spring. All right, so what we end up with here is a formula. And that formula is that the force that's applied is going to be equal to that K value times our displacement. Now, this is from the point of view of the applied force. But often we really want to know, well, what is the spring force? And so that's going to be equal but opposite. So a negative K times x. So these are going to be handy formulas to either figure out what the applied force needs to be, what the displacement is going to be, or what that spring force constant is. All right, now in addition to looking at that linear relationship, we could also look at the integral, or the area underneath that curve. All right, and as you can see, I've colored it in here a little bit. All right, it is in the shape of a triangle. All right, and we know that the integral is also the area under that curve, and in this case, the area of a triangle is 1/2 base times height. All right, well, if we look at what our base and height are here, the area is equal to 1/2 the force applied times our displacement x. All right, so let's think about the units that we get from this. All right, if I were to take newtons and displacement, I'm going to get a unit of newtons times meters, and that should be familiar. We've talked about one other variable that has that unit. All right, so the area under our curve is actually telling us the work that is being done to stretch or compress the string. All right, so the work is equal to 1/2 of our applied force times that displacement. All right, but you're not going to see work written this way very often for these variable forces. Instead, they're going to go and take this formula for force that we found earlier, and they're going to say, okay, the work done by this applied force is 1/2 of K times X squared. All right, so this is the formula for the work done by a variable force. All right, now what if we didn't have that formula, or we didn't have the integral of this space? Well, what we could do is just look at our axes and take the base and then half the height, and we could calculate it directly ourselves. And that happens quite a bit in these problems. All right, so again, we've got two new formulas. All right, we've got our formula for work in the presence of a variable force, and then we've got our formula for force in the presence of a variable force. Again, remember, we tend to use these most often in the presence of springs and rubber bands because they require more and more force the more we stretch them out. All right, so let's try using these new formulas. All right, so to measure the spring force constant, of a spring, we add a 0.65 kilogram mass to the spring, which stretches it by 6 centimeters. What is that spring force constant? All right, so I have a mass of 0.65 kilograms. I've got stretches, so there's my x value, 6 centimeters, so that's 0.06 meters. Please watch your units. And we're looking for K. All right, now we're going to assume that this is this particular setup, all right, where we've got a vertical spring, a spring hanging from some sort of hook or rod, and then we have added mass to this bottom piece. So that means that we're going to have a gravitational force pulling down, opposing that spring force that's trying to pull the spring back up. All right, so that means my applied force here is going to be that Fg value. All right, so I know that that applied force has to be equal to the spring force constant times my displacement. All right, so Fg is going to be equal to 0.65 times 9 point, well, times 10. We'll do 10. So 6.5 newtons. Now, if you're in the lab, you should not use 9.8. Don't use 10. 9.8 is more accurate. All right, and then our displacement of 0.06 meters. All right, so our spring force constant here is going to be around 108 newtons for every meter. All right, now you might say, well, that seems large. It's not. Spring force constants tend to be greater than one, not always. All right, but I've seen them as far up as 1,000, 2,000 newtons per meter. I mean, springs can be very, very tightly wound, and they can be very difficult to elongate. So you might need a lot of force to get it to move. All right, so having that force is not, don't let the math guide you, don't overthink it. All right, for part B, how much work has been done on the spring? All right, well, we know that work is equal to 1/2 of K times our X values squared. All right, so we have all those numbers. So 1/2 of 108 newtons per meter times 0.06 meters squared. All right, so we are going to do 0.194 joules worth of work as we stretch this spring, the 6 centimeters. Okay? All right, so that's one example. Let's try another one. All right, here in the lab, you set up a spring with a hanging mass. So that's the same picture that I had above. The spring has a constant of 75 newtons per meter. What is the work required to stretch the spring 10 centimeters? All right, so I'm going to have a force due to gravity standing in as my applied force. All right. I'm going to have a K value, X, and I'll be looking for work. All right, so my K value is 75 newtons divided by meters. I'm going to stretch it 10 centimeters, so that's 0.1 meters. And I'm asked to find work. Oh, actually, I don't need Fg. Sorry about that. Let me slide this up a little bit. All right. All right, so that's all I need for work. So work is going to be equal to 1/2 of K times X squared. All right, so 1/2 of 75 newtons per meter times 0.1 meters squared. All right, so the work being done here is 0.375 joules. Okay, great. Next, what is the work required to stretch the spring an additional 8 centimeters? Okay, so we've still got our same K value, 75 newtons per meter, but this time our displacement is going to be a total of 18 centimeters. But it's not asking for the whole 18, it's saying for this additional 8 centimeters. All right, so what we really need to find here is the change in work or the difference in work, not the work just for the 8 centimeters. All right, you may ask why. All right, so let's see if we can visualize this. All right, I'm going to draw it this way just because it's easier space-wise. All right, so let's say that we've stretched this spring out. Here's our 10 centimeters, and that took 0.375 joules of work to do. All right, now we want to take it out an additional 8 centimeters. So I've gone 10. Now I want to do it even further. Now remember what we said. This is a variable force. So it's not the same amount of force needed for each centimeter that we stretch it. It's the amount of force increases for every centimeter that we stretch it. All right, so this is going to be harder to do, all right, which means we can't just calculate it for 8 centimeters and call it good, because that value would only be for starting from our original position and going out 8, not being at 10 centimeters and then going out to 18. It's very different. So you have to be careful. All right. So the way I like to think about it is I need to figure out the work to go from 0 to 10 centimeters. And I did that already in that part A. So that was 3.75 joules. And then I need to figure out the work to go from 0 to 18 centimeters. All right. So to calculate that, 1/2 of 75 Newton meters times 0.18 meters squared. All right, and that's equal to 1.75 newtons. So you can see that's a big jump from 0.375. So you can see how that value is not going up the same increments per centimeter. Okay, now to figure out the answer to our question, what I really want to know was what is the work to go from 10 to 18 centimeters? And to figure that out, I'm going to take the work from 0 to 18 and I'm going to subtract the work needed from 0 to 10. That's basically what we're doing. All right, so 1.75 newtons minus 0.375 newtons, and that's going to be equal to 1.375 newtons. Okay, if I'd calculated it just for that 8 centimeters, all right, I would have said, okay, so I have 0.08 squared times 75 times 1/2, I would have gotten 0.24 newtons, which is way less than 1.37 newtons. So make sure if it's asking about additional displacement, right, you're going to have to find the difference between the two positions starting at the initial point. All right, do not just say, oh, it's stretched an additional 8 centimeters. I'll just find it for that 8 centimeters because the math is going to work out so that you're really starting from 0 to 8, and it's very different. Okay, all right, last one. Right here, we're investigating the effect of a variable force on work, producing this plot. Based on the data, calculate the work done. All right, so here we have a plot. We haven't been given a lot of numbers, all right, but we remember from our lab that the area under the curve equals work. All right, so what we're going to do is look at these two different triangles and we're going to calculate the area of each of them. We have this triangle and then we have this little triangle. All right, up here we're all positive force values, so this is going to be positive work, and down below we'll have negative force values. This will be negative work. All right, again, remember the area of a triangle is equal to 1/2 the base times the height. Okay, in this case, the base is our displacement value and the height is our force value. All right, so we're going to do it for triangle A first. All right, so our work is going to be equal to 1/2, and then we go look at the base of this triangle. It goes out to 8 meters. And then we look at our maximum force value. It's 400 newtons. All right, so we're going to have a value here of 1,600 joules. So that's the amount of work that's been done based on this plot for triangle A. All right, then we're going to look at triangle B. All right, work again is 1/2. The base this time is 3 meters. And our height is negative 200 newtons. All right, multiply those together and we get a negative 300 joules. All right, so then our net work is going to be equal to the sum of those. So 1,600 joules plus a negative 300 joules, and we get 1,300 joules as our net work. All right, so if you're ever given a plot like this and you're asked to find work, the easiest way is to figure out the area under the curve. Now, just as an example, because these have popped up every now and then, let's say that our plot, here's our force, looks something like this. All right, so this time you have to be a little creative. All right, we've got a teeny bit right here of constant force, which is fine. All right, we just need to split this upper piece into three pieces: a triangle, a rectangle, and a triangle. And then we're going to treat it just like we did above. For the triangles, we know that the area is equal to 1/2 the base times the height, right? For our rectangles, we know that the area is equal to just the base times the height. So you'll use the tick marks on the graph to figure out those area values. And then of course, D is just a triangle. So we use 1/2 base times height. So don't get frightened. Frightened's not the right word, but don't get nervous if you see a shape for one of these force versus displacement graphs that's not just triangles. All right, we could have a little bit of constant force in there, which is okay. All right, and you just treat it like a set of shapes, and you look at the area of each of the shapes. Okay. All right, so again, this was looking at work when variable force is being applied, and that's going to come into play when we have springs and rubber bands.